Hello, and welcome back to Learning with Lee. In today's episode, we'll continue talking about structs, linked lists, as well as reintroducing our earlier topics of merge sort and dynamic memory allocation. In the previous episode, I showed you a fair amount of what we could do in terms of the different functions that we had for both the list, the links, as well as then also the sorting. And there's a few changes I had to actually make between the last episode and this one to make sure that everything worked correctly. So I'm going to cover those first before I get into the difference in terms of how our dynamic memory allocation is impacting our performance. For starters, the first thing that I had to do was over in here, though technically this wasn't the first thing I did, but one of the things I had to do was create this append function. And it wasn't strictly necessary. However, there was a bug that was occurring on the merge algorithm in here during this step. And previously what I was doing was I was inserting and popping off whatever happened to be the first item in the second list. Unfortunately, that could result occasionally in some of the elements being transposed, so as that in case you had, say, one number that was 150, one number that was 100, even though it should pop off 100 first, it would wind up basically popping off one and swapping the order of them. So I created an append function which just takes in a second linked list. And as I had mentioned in the previous one, rather than going through the entire while loop, this is something that I hadn't covered in loops yet, and I use what's known as a break statement. And the break keyword and the break statement lets you basically go, if I'm in a loop or if I'm in some other form of scope such as this, you can't really do it for an if-else statement, but when we get into switch statements, you'll see that they're used there. But for while loops, for for loops, and do while loops, you can end up using the break statement to effectively jump out of the loop and go down to here, and whatever happens to be next. So it's a bit of an ugly thing. In general, you don't want to use break statements throughout your code, but for this case here, it was an easy enough change and easy enough fix for it. And in here, what it does, and these are just to make this a lot cleaner throughout here, because I could just, reuse these pointers everywhere I end up using it. However, it's a matter of, it's a bit easier to see what I'm doing here. So, the first thing is that I'm just, as you can remember in our sort of thing in which we viewed them as bracelets or circles, and what we ended up doing was that you basically end up splitting open one end and you end up tying in the other one. So we basically tie the end of, in this case here, our target, which is the list that we're going into and depending onto, to the start of whatever our list was that was the source. And then we end up basically tying in the other end, and it's good enough in order to do that with these 4 pointer assignments. Then the other important thing is that we have to update the count in list, because otherwise that'll lead us into errors when we're printing it, when we're dealing with some of the sorting, etc. And then we have to clear out the source list. And that prevents, when we end up, in case we delete this pointer, it allows us to avoid having any issues of it accidentally deleting items that are in this list. Then the other thing that I had forgotten to do originally, and had actually showed you this, was that down in here, in our split list, and I changed it a little bit just to make it cleaner, similar to how I did with the other one, that I added in this link pointer here. It doesn't really change anything other than making it a bit easier to read. And the major change that was down here, I had mentioned it, I believe, in the previous episode, but I had actually forgotten to include in the implementation, which is that we need to update the counts of the list. And the way in which you do that's relatively easy. The source gets the half count, and whatever you split off gets the previous count minus the half count. So, relatively easy. And those were really the major changes I had to make to this in order to get this working and fix a couple of little bugs that were in there. So, as you can see down here, I've already actually run this once. And just to sort of demonstrate it again, I can rebuild it. It says I have nothing to build. Run it again. You can see that outputs the list down here. And then you can see how much longer, though, it is for our linked list than even our array up here, which is using malloc and the like, And some of that's because of the fact that we have to iterate over our list on every one of these merges, as well as also, more importantly, on every one of the splits. So every time that we end up going through here, and we have to do this iteration here to actually find where we need to split, that gives us significantly more work than what we had previously when we just were doing this with an array. As well as also the fact that we end up having to update 4 pointers effectively, and in some of these cases, we also have to update this one, the 5th pointer of the first item in our new list here, that happens to be used for making certain that we can actually see the second linked list. So those end up also adding an additional overhead that we didn't have to deal with as much in the previous one. The previous one, it just was we had to maintain effectively 2 pointers rather than 4. So that's where a lot of our overhead in this is coming in. And you can imagine that even though we're doing this for a fairly decent sized list of integers, in this case here, 100,000, the issue is that for more complicated comparisons and the like, we're going to eventually really start noticing this difference in efficiency between arrays and linked lists. And that's one of the things to understand, is that additionally, we're also using significantly more memory, because if we take a look at our structs here, an array is just going to go, I just have a whole bunch of items in it. It doesn't need to have effectively these 2 link pointers for every item in there. It doesn't need to have this additional count and link pointer at the very beginning. So as a result, we basically have either, depending on the size of these, let's just say for now that they happen to be the same size as an int. However, realistically, they probably are twice the size of an int. So we've either tripled or quintupled, so either times 3 or times 5, the size of just an int array. Plus a little bit extra because of these down here, though that's rather negligible in the grand scheme of things, considering that we're adding in 200,000 link pointers compared to only 2 of these. So that happens to be a major difference in our memory footprint. And it's one of the reasons why, in case, as we might do in the future, you might want to consider having something that considers the size and scope of your list, as well as whether or not it's necessary for you to actually have the second link pointer here. Because if we only had a singly linked list, then we would only either be doubling or tripling, depending on whether a link pointer is 1 times the size of an int or twice the size of an int. But it's important to remember that this is a pointer, not the actual struct length. Because that would end up being a bit weirder in terms of how that would end up working out. So that happens to be where we're getting a lot of our inefficiencies. So one of the things we can do with this, though, is we can actually change it so that we don't end up using as much of the heap. We still will end up using the heap, but basically what we would do is we would create a list, split list. And I believe that I ended up just naming it, linked list. So we're going to create a linked list as our split list. And then we're going to modify split list to take in that, as well as, split to take in 2 of these. For this case here, I'll just pass in that so as it effectively gets treated as a link pointer, because I'm passing in the address of it. And that's how you can basically create a link pointer. So I don't have to change merge sort recursive or merge. Those are just fine as they are using link pointers. However, I no longer need also to delete the list, so I don't need to go through and free up that memory, because that's automatically going to happen as soon as I'm done leaving this scope. So let's head on over to split and make that change for it, and we can see how it's going to impact our efficiency here. So what I can do is I can just take this, copy it up to here, and really I can then also just make this void, because there's not really any need to have it returning the split list, since we're already passing it in as an argument. And then in here, what we can do is we can see all this, spots where we end up using it. We use it down here, use it down there. So that happens to be perfectly good, and that's really the only change we had to make other than making the change in the header file. So if we head over here, actually, the quick way is just you copy this line, head over to your header file, head on down to split, and paste that in. And then that should be all that we need to do. Yep, and run it. And there we go. And as you can see, it honestly didn't save us too much room. And that's because of the fact that, as I had mentioned, we're already effectively doing twice as much work as this one in terms of having to update these pointers. Because in the other case, when we're effectively having our, if I head on over to array utils in here, oh wait, what was this one complaining about? Oh yeah, good, there, stopped complaining. Occasionally it's going to show you those little errors there, and as soon as you open up the file, it's going to be like, oh no, my bad, I thought that was an error, but it actually isn't. And that's because of the fact that I hadn't yet updated the header definition, but now that I have, it's, and well, as went back to this file, which is the trick, is that you have to actually go back to the location of the error, and that's like, oh, okay, yep, this is good. But if we head on over, not to array utils, over to sort, and take a look at some of the stuff that we have in merge sort or merge sort alternative, and if we head down in here, you can see that down in here, we only are dealing with a few integers. We aren't having to deal with basically what ends up being 4 pointers and then effectively a 5th pointer when we end up assigning the one from our split array to one. So that ends up creating a significant amount of overhead. There might be some ways in which you can end up reducing some of the complexity here, but unfortunately, linked lists aren't a really great data structure to use for sorting. They're not abysmal, but at the same time, they aren't as good as something such as an array, or, as we'll eventually get into, something that C++ already provides you, known as a vector. And you might be thinking in terms of vector math, and it's sort of similar, but at the same time, it is also different. And really, what I would like you to do is spend some time, look through this, see if you can understand the different changes I made, and I'll continue to discuss the major couple of things I've left out over the course of these episodes, dealing with how I'm outputting this stuff properly, as well as also how I'm generating the random lists in the next episode. Thank you very much for watching. I hope you have a wonderful day.